talking about what gravity is in the ultraviolet sector. So at least in classical theory, we know that we have in GR we have Big Bang and black hole singularities. So at these points, we don't know how to make sense of physics. So it shows that we need some sort of UV completion in order to understand gravity at very short distance scales and very short time scales. And even at the quantum level, we know that GR is non-renormalizable. Well, it was shown that it is renormalizable. Pure GR is renormalizable at one loop, but from two loop onwards, it's not renormalizable. And this was shown back in the mid 1980s. So you need to add counter terms that are curvatures of higher order, like r squared and r cubed and so on, if you want to absorb all these divergences. And also, just in the basic spirit of effective field theory, you should include all possible high dimensional operators in the action, which are consistent with the symmetries. So in this sense, in this case, in the case of gravity, the symmetry is general coordinate invariance. So all the operators consistent with that symmetry must be included in the action if you want to make sense of UV physics. These high derivative operators are the operators that will become more and more important as you go to higher and higher energies, and you should include them if you want to describe physics at these very short distance and time scales. So this idea was taken seriously by Stell in 1976, where he considered adding higher curvature terms to the Einstein-Hilbert action. So if you take the Einstein-Hilbert action, which is the first term over here, and you add r squared and r mu nu squared terms, you get this quadratic curvature gravity action. You can also add a Weil squared term or a Riemann tensor squared term, but in 4 dimensions, you can get rid of it using the Gauss-Bonnet identity, which is the total derivative and in 4 dimensions. So he showed that if you expand this around flat space, this theory is actually renormalizable, but it has a problem in the sense that if you find out the degrees of freedom that you have in this theory, you will have the usual 2 degrees of freedom coming from the plus and cross polarizations of the graviton. Then you have a massive scalar, which contributes 1 degree of freedom. And you have a massive spin 2 degree of freedom, which is actually a ghost. And this has 5 degrees of freedom because it is massive spin 2. So a ghost degree of freedom, there are many ways of looking at what a ghost degree of freedom means. In one sense, it's basically a degree of freedom which causes the Hamiltonian to be unbounded from below. So if you have a system which has a Hamiltonian bounded from below and it interacts with a system which has a Hamiltonian unbounded from below, this will cause an instability of the vacuum, both classically as well as in the quantum sense. And this will lead to runaway production of particles, infinite production of particles, and this causes instability of the vacuum. So this is something that you should not have in the theory. So this is a sick degree of freedom. So even though this particular model of quadratic curvature gravity comes with improved properties of renormalizability, comes at the cost of unitarity. Ghost degrees of freedom also, they lead to loss of unitarity in the sense that they give rise to negative normed states in the quantum sector. So you don't want that. So the upshot is there a way to retain the UV stabilizing abilities that you have of these high derivative terms, but at the same time avoid introducing these new or sick degrees of freedom? So this is at the level of the action. Now let me consider a physical scenario, which is bouncing cosmology. So bouncing cosmology, from the beginning, it avoids the Big Bang singularity problem because you have a phase of contraction which precedes the expansion through a finite value of the scale factor at the bounce point. So the scale factor never goes to 0 at t equals to 0, and the universe is initially in a very large, it has a very large extent, and then it contracts through a finite value of the scale factor. There is a finite value, there's a finite size of the universe at t equals to 0, and then it starts expanding again. So how can we achieve a bounce just in general relativity? So that's very easy to see why it needs some sort of exotic matter. For that, you just need to see what the Friedmann equations look like. So at least for spatially flat backgrounds where k is 0, the Friedmann's equation is given here in equation 1. So you see that h dot is proportional to minus of rho plus p. So if you want to bounce, you need to go from a phase of contraction to a phase of expansion, which means that h has to go from negative to positive, which means that h dot on the left-hand side, this has to be positive. So for h dot positive, you need to have rho plus p negative. which is basically a violation of the null energy condition. And NEC violation typically implies ghost or gradient instabilities in your theory, which is again something that you do not want. So this is not the approach that I will follow. There are many models of bouncing cosmology. You have matter bounce cosmology, bounce using Galileons or ghost condensates. You have bouncing models in loop quantum gravity, in string cosmology, the pre-Big Bang scenario, ekpyrotic models. There are many models, but the approach that I will follow is that I will keep my matter sector intact. It is the usual standard model, but I will follow the approach that gravity itself must be modified at very short distance scales and very short time scales, such as near the beginning of the near where the universe is very has a very near t equals to 0, where the bounce happens. At least at those times, you should include higher curvature terms in your action to account for the physics at those very short distance scales. So that simply amounts to adding these high derivative terms like r squared and r mu squared in the action, in addition to the Einstein-Hilbert term. This again leads to ghost instabilities, like I explained in the previous slide. And it is actually possible to have bouncing solutions in a theory like r plus r squared plus lambda, but they suffer again from some problems in the sense that if you need to add some matter here, and if you add radiation, you'll see that the energy density component of that radiation is negative, or you will have ghosts in the theory. Ghosts in the sense, so you will have a coefficient here in front of r squared. So either this coefficient is negative, which means you will have a ghost scalar mode, or you will have radiation energy density, which is negative. So in whichever way you choose, you will have an instability in the theories, which is what we do not want. So again, the upshot is how can we capture UV physics from high derivative terms without introducing pathologies? So the approach that I will follow is to non-localize the action. So non-locality, in a very general sense, has been a natural feature in many approaches towards quantum gravity, and it appears in many different ways in different theories like string theory, non-commutative geometry, loop quantum gravity, asymptotic safety, and causal set theory. They appear in all these different theories in different ways, but it seems to be a common feature. And non-local field theories as UV finite theories have a very long history that goes back at least to a work of Born in 1949, where he doesn't consider gravity, but he considers electrodynamics. And in that case, this is a snapshot from his paper in 1949, where he considers ultraviolet modification of the equations of motion of Maxwell's electrodynamics. So this AK is the potential for electrodynamics, and usually you will just have p squared AK, but you have this exponential of minus p squared factor as well, which modifies the UV content of the theory. But an important point to note is that this exponential of minus p squared does not introduce any new poles. The only pole that you will get is from the p squared sector. So at p squared equals to 0, you have a pole. But exponential of minus p squared, although it modifies the UV sector, it modifies the equations of motion. It does not introduce any new degrees of freedom, and therefore it does not introduce any ghost degrees of freedom as well. And this was done in the case of electrodynamics, and later it was extended to gauge theories, and people have also studied in gravity as well. So the idea is that instead of truncating terms to a finite order in derivatives, which typically introduces ghost instabilities, one can try constructing suitable terms which contain derivatives to all orders. And this actually does appear in a natural context in string field theory and p-adic string theory, where in the action you will have terms of this particular form, where phi is some scalar field, let's say, and you will have this exponential of box by m squared term. So this box is just the usual g mu del mu, and m is some high energy mass scale. So this is a non-polynomial term. You have derivatives to all orders. You're not supposed to truncate the series at any order, and you will have derivatives all the way up to infinity. So this is the inspiration that I will take and to try to modify GR in the UV sector in this way. So the action for gravity that I will consider is given here in equation 2. It's the usual Einstein-Hilbert term with a cosmological constant and an r squared term, but a non-local r squared term. So you have this f of box, which is an unknown function. We will get to what it means later. but this f of box is sandwiched between these two Ricci scalar terms. So inspired from this non-local theories in other contexts, this f of box is a function with unknown coefficients f of n, but the important point is I will consider an infinite series of derivatives. So this box is g mu del nu, and you have a sum all the way from n equals to 0 to infinity. And since for dimensional reasons, you need to have a new mass scale, which I will call ms, which is I'm assuming that it is less than the Planck scale, which I assume to be the highest scale in the universe. And I need to have an infinite series of derivatives here, because if I truncate it to any finite order, let's say 2 or 3, then as we've seen, for example, in Stell's quadratic curvature gravity, you will have ghost degrees of freedom, so which is what we do not want. So the idea is to, if the question is, if we start with this UV modified theory of gravity, is there a way to fix these functions f of box such that you can retain the UV stabilizing aspects of these high derivative terms, but at the same time avoid any new or ghost degrees of freedom other than the spin 2 massless graviton? And we will see that it is indeed possible to do so. These are the equations of motion that you get from varying this action with respect to the metric. It's not very important what these factors of k mean, but it's just the definition what you get. So in equation 3, you can see that you have these factors of f of box everywhere, so which is an infinite series in derivatives. So it seems very complicated, and a priori you don't really know how to solve these equations. Even solving Einstein's equations is very hard. So in order to solve these equations, you need to assume some sort of symmetry or in your background, or you need to assume some sort of, you need to take an ansatz to solve these equations, and that is what we will do in a few slides. So there is a 3-step process to finding stable solutions in non-local gravity. First is to find background solutions that can solve the equations of motion, and then we want to study what perturbations around this particular background look like. Firstly, we need to look at what it looks like at the linearized level, at the equations of motion, or at the level of the quadratic action, before going on to nonlinear corrections. And the third point, and the most important one, is to deduce the structure of this background dependent form factors. So this f of box depends on the background around which you're expanding. And is there a way to fix these form factors f of box such that the perturbations around this particular background can be made free from any kinds of instabilities, which could be ghost-like or gradient or tachyonic? And we will see that it is indeed possible to do so. So in order to solve those horrible, complicated equations of motion, I will assume an ansatz, which is given here in equation 4. So I assume, by the way, I have a bar over box and R. This just means that it indicates that it's a background. And also another thing is that there is no matter in the theory that I'm considering. So the theory is purely gravitational. So you have the Einstein-Hilbert action, which you have the Einstein-Hilbert the Ricci scalar, and you have the cosmological constant and a non-local R² term, and there is no matter at all in this model that I will consider. And that's why I'm saying that there is the stress energy tensor is 0, so it's vacuum. And I will impose an ansatz on the background Ricci scalar, and I will say that the background satisfies this equation, that box R is R1R plus R2, where R1 and R2 are some constants. This equation is actually just the trace equations of motion of the theory, where f is just some constant. So for local R plus lambda plus R squared without this f of box, if you take the trace of the equations of motion, then you just get exactly box R equals to R1R plus R2. So the idea is to take this trace equation of motion and then plug it back into the non-local equations of motion, and then see if it is possible to satisfy the equations of motion for the non-local theory. And you can do that. If you assume this ansatz, if you pick this ansatz, then it's very easy to, the equations of motion simplify to a very good extent, and because all these f of box factors that act on this background R will simply reduce to these simple factors of f1 R plus f2, where f1 and f2 are just some constants. So they defined over here where f1 is just this function evaluated at the point r1, and f2 is some constant divided by another constant multiplied by f1 minus f0. And this f0 is basically the first coefficient in this power series expansion of f of box. So these are just some numbers in the f1 and f2. If you substitute this ansatz in the equation of motion in vacuum, then you get some unique conditions on the form factor that must be satisfied if you want to satisfy the equations of motion, and they turn out to be the one given here in equation 7, which means that which amounts to f1, which is f evaluated at this point r1. This has to be 0, and the derivative of f at r1 also has to be 0, and f2 is related to the Planck mass, and importantly, this cosmological constant is related to the first coefficient f of 0 in this expansion of f of box in this particular way, which we will get to later, is actually important. And from equation 6 and 7, the sign of f and 0 of f0 and the cosmological constant are related to each other. So if you have a positive cosmological constant, then you will have a negative sign for the first term in this f of box, and the opposite if you have a negative cosmological constant. So now we want to see what the quadratic action looks like around this particular background. So I will take the action that I have for non-local theory, which is this one. So you have Einstein-Hilbert term, cosmological constant, and a non-local r squared. And I will vary this action around this background. So I will. So I'm assuming that. So I'm fixing that the background satisfies this ansatz, box r equals to r1r plus r2, and I will impose not all, but two of these background conditions that are given here in f1c equals to 0 and f2 equals to minus mp squared by 4. So schematically, the quadratic action looks like this in equation 9. So from here you can see that actually only the first term was capable of producing any propagating vector or tensor modes, because they come from the quadratic piece of GR. So delta GR is the quadratic variation of the Einstein-Hilbert action. But it just so turns out that if you impose these conditions, which just follow from the background equations of motion, then this exactly cancels with this second variation of the Ricci scalar. So any source of propagating vector or tensor modes is exactly cancelled because they come with the same coefficient and opposite sign. So the first term in this action, which it actually kills any source of propagating vector or tensor modes, and all the other terms starting from this lambda all and all the terms in the second row, they will lead to only a scalar degree of freedom. We will get to that later, and either they will lead to only a scalar degree of freedom, or in this case, well, you have a term here, the term in parenthesis here, that will also have tensor or vector modes, but they don't have derivatives, so they will not lead to any propagating vector or tensor modes. So if you impose the remaining background conditions, I imposed only two of these, f1 equals to 0 and f2 equals to minus mp squared by 4, but you have these remaining conditions as well, where f1 prime has to be equals to 0 and lambda is related to f0 in this way. If you impose all the conditions on the background, then after a considerable amount of algebra and massaging the quadratic action, it reduces very simply to this equation 10. So it looks like there is only one term, zeta z of box times zeta, where zeta is defined over here. So this is delta of box acting on r bar plus box minus r1, where r1 is some constant, multiplied by delta r. And z of box is related to this unknown function f of box in this particular way. So now I should mention that at this point, I have not assumed that the background is spherically symmetric or if it's FRW or anything. So I just assume that it satisfies, I just impose that it satisfies this ansatz, box r bar equals to r1 r bar plus r2. So if you want to see more clearly what the degrees of freedom are in this theory, then you need to fix the background. So I fixed the background as FRW. In this case, if G bar is FRW and H mu describes perturbations, then you can use standard 1+3 cosmological perturbation theory, where you can decompose your H mu in terms of scalar vector and tensor degrees of freedom. After gauge fixing, well, in the longitudinal or the Newtonian gauge, you will have two scalars, two vectors, and two tensor degrees of freedom, which are given over here. And it's very easy to see that the zeta that you have in the quadratic action is purely a scalar degree of freedom, and it's composed only of phi and psi. It's a linear combination of phi and psi, and there are no tensor and no vector degrees of freedom in this theory around this particular background. So now the question is, if this is the quadratic action and you have one scalar degree of freedom, this kinetic term for zeta is still unknown, and that's where that's the main question. So can you fix this kinetic term for zeta such that you have no extra degrees of freedom and no ghost degrees of freedom in the theory? So is it possible to fix this z of box in to avoid any instabilities? And it is possible to do so. So if you want to have a theory which has no extra degrees of freedom or ghosts, just by looking at the quadratic level of the action, we impose that the kinetic operator for the modes should have at most a single zero. And for this, I will use a simple mathematical theorem, which is the Weierstrass product theorem, which says that exponential of an entire function, where gamma is it could be any entire function. The simplest entire function is just box itself, but otherwise it could be anything else. So an exponential of an entire function does not introduce any zeros. So the only zeros that you will get, so it's given here in pink. So if you choose z of box like this, box minus m squared times exponential of gamma of box, the only zero that you will get is at box equals to m squared. And this exponential factor, although it modifies the UV sector, it does not introduce any new degrees of freedom, and therefore it does not introduce any ghost or unstable degrees of freedom as well. And the kinetic term for zeta also has the correct sign to avoid ghosts. So this is the appropriate choice for f of box that you need to have in theory if you want to avoid any ghost or new degrees of freedom. And the only propagating mode is this is the scalar zeta, and it's free from any ghost instability. But it depends on the sign that you have for cosmological constant. If it's positive, then you need to choose. Then you need to have f of 0 negative, which f of 0 is the first coefficient in this expansion of f of box around box equals to 0. So for a positive cosmological constant, you need to choose your f of box as it is given in equation 13. But if you have a negative cosmological constant, you need to have a positive coefficient for this first term in f of box, and for this the choice is given in equation 14. And in this case, z of box, which is the kinetic term for the mode zeta, it has no zeros at all actually, and it acts like a p-adic scalar, and it doesn't propagate because it does not have any zeros. So now we want to see some particular examples of bouncing solutions that satisfy the ansatz, which so we need to satisfy the ansatz box R equals to R1R plus R2, which is the ansatz that I assumed at the level of the background. So there exists some two bouncing solutions given over here, which solve the ansatz, and their vacuum solutions. They solve the vacuum equations of motion of the non-local theory. And as I just showed, if you compute the quadratic action, they contain only one single ghost-free scalar mode and no vector or tensor modes at the around this background at the linearized level. And two examples are this cosine hyperbolic bounce, where the scale factor goes like a cosh, and for this you need to have the cosmological constant to be positive. This kind of a bouncing solution actually becomes de Sitter at very late times or very early times, because cosh goes like exponential at very late times. But it is a bouncing solution, so the scale factor never goes to 0 at t equals to 0. And another solution is an exponential bounce, where the scale factor goes like exponential of t squared. And in this case, you can have both signs for the cosmological constant. So there are two known bouncing solutions, which satisfy the ansatz and which can be viable models for a bouncing background in this non-local theory. So I will fix the background to be a cosine hyperbolic for the time being. In this case, the cosmological constant is positive, and the quadratic action looks like as it is given in equation 15. So there is only one degree of freedom, which is zeta, which in 3+1 cosmological perturbation theory can easily see that this is just one scalar degree of freedom. And you have one pole, 1 0 that comes at box equals to m squared, and this exponential factor, exponential of gamma of box, where gamma is some unknown entire function. It cannot be fixed at this point, but the simplest, as I said, the simplest choice could be just box itself. This is the quadratic action for the scalar mode around a Cosh-like bounce. And if you want to have a stable bounce, we need to see what the scalar mode behaves in time all across the evolution of the universe. So for that, you vary the action with respect to zeta, and you get the equations of motion. You will get an exponential of gamma of box to the left hand side over here. But since I'm only considering a homogeneous equation, it's on the right hand side, it's 0. So this exponential factor actually, you can effectively just remove it. And the equation of motion that you need to solve for zeta is simply just 16, where this box bar means that the background is an FRW background, where the scale factor is given by this cosine hyperbolic term. And it is easy to solve this equation. And you will see that in Fourier space, all across the evolution, all across different times, all the way from -infinity to +infinity, the scalar mode, the Fourier component of the scalar mode zeta k, it is oscillatory, and it's bounded all across the bounds for different values of the wave number. So it does not blow up at any finite point of time, and it indicates that the scalar mode is stable all across the bounds. So this brings us to the end of the first part of the talk. So the upshot is that there exists a higher derivative non-local gravity model, which where you have a unknown function f, which is sandwiched between two factors of the Ricci scalar, which admits non-singular bouncing solutions in the absence of matter. And there exists a special vacuum, which is T-zeta at late times for a cosine hyperbolic bounce, with only a scalar propagating degree of freedom and no vector or tensor modes at the linearized level. I'm saying this is a special vacuum because typically you would expect that there will be gravitational waves, but it turns out that in this case it does not. That's precisely because of the background, the conditions that you have on the background. And it is actually indeed possible to have special vacua where you do not have tensor degrees of freedom. And it is possible to choose a suitable function f such that the scalar can be made free from ghost instabilities around this dynamical background, and the evolution is oscillatory and bounded across the bounds. But obviously there are some open questions. The first question is the quintessential question that comes up when anyone considers bouncing models is the isotropic and homogeneous solution is it stable with respect to is it stable when it comes to anisotropy? So this is well known as the VKL instability, where anisotropies grow larger than matter and radiation and spatial curvature as the universe contracts, and as the scale factor it becomes very, very small. Anisotropies grow very, very large, at least in GR. So the question is, at least if you have this growing anisotropies, the problem of growing anisotropies in GR, can you avoid this problem in non-local gravity? And this is something that we're currently looking at. And another question is it also possible to have non-singular bouncing scenarios in much more general actions, which not only include the Ricci scalar, but also non-local Ricci tensor and non-local Weyl squared terms? And again, this is another open question at this point. So now I'll start the next part of my talk, which is based on the paper that came out in 2019. In that paper, we made a very general analysis of scalar vector tensor perturbations in non-local gravity. And in particular, we focused perturbations around non-maximally symmetric backgrounds. Typically, when people do perturbations, they either do around flat space or de Sitter or anti-de Sitter, or they do it around FLRW backgrounds. So the higher the symmetry you have in the background, the easier it is to do perturbation theory and to find the kinetic matrix and the different scalar vector degrees of freedom. But as you move to more and more non-trivial backgrounds, uh, the analysis becomes much more complicated. So we wanted to see if it is possible, again, to find backgrounds which are not maximally symmetric, but still, if it is possible to find some functions, these non-local functions in the action, which can make the perturbations free from any ghost-like instabilities. And I will get to an example where it is indeed possible to do so. It is very easy to see why. It is easy to see how to go beyond maximal symmetry. So for that, you just need to decompose the Riemann tensor in terms of its fully traceless and traceable components. So the first term is basically just the Riemann tensor for de Sitter and anti-de Sitter or anti-de Sitter spacetime. And in the second row, you will have terms composed of the Weil tensor and the traceless Ricci tensor. So this S mu is the traceless Ricci tensor. So this indicates any sort of deviation from de Sitter or anti-de Sitter. So if you want to go beyond DS areas, then you need to either turn on your Weil tensor or you need to turn on your traceless Ricci tensor. So the background that I will choose in this talk will be one which is conformally flat. So the background Weil tensor is 0, but the traceless Ricci tensor is non-zero. So even though it is conformally flat, it is not maximally symmetric. And I will also assume that it satisfies this covariantly constant condition. So the covariant derivative of the traceless Ricci tensor is 0. Well, one of the reasons for considering this is simply because it simplifies the analysis of perturbations and computing the quadratic action and so on. Otherwise, the computations are very cumbersome. So the only thing that separates me from non-maximal symmetry is this non-zero value of the traceless Ricci tensor. And all the computations that we did, if you simply take the limit of the traceless Ricci tensor going to 0, then you go back to results in DS and ADS spacetimes, which were done a couple of years ago, and we recovered all the known results. There's another physical motivation for choosing these conditions, is that at least in generic scenarios, these conditions can be realized near the bounce point of a sufficiently slow and symmetric bouncing scenario. So I think it's easy to see this from a Venn diagram, what the kind of background that I'm choosing. So on the right-hand side, you have the Einstein spacetimes, where the traceless Ricci tensor is 0. These are the spacetimes that people consider for black holes, for instance, for example, Schwarzschild. So the right-hand side is relevant for black hole physics. And on the left-hand side, you have conformally flat spacetimes, which is relevant for cosmology, where the Weil tensor is 0. And the intersection is where you have de Sitter and anti-de Sitter spacetimes, which is the maximal symmetry you can have. So the background that I will choose is the one which is conformally flat, but it has a non-zero traceless Ricci tensor, but the covariant derivative of the traceless Ricci tensor is 0. And the first condition on the constancy of Ricci scalar actually follows from this equation, just using the Bianchi identity. So this first equation is not an extra condition, it just comes from the second one. So I want to see what are the degrees of freedom in non-local gravity in these non-maximally symmetric backgrounds, and if it is possible to have degrees of freedom which are free from any instabilities. So for this, I will use a covariant scalar vector tensor decomposition, not the 1+3 cosmological perturbation split. In this case, I will covariantly split the perturbation h mu nu in terms of a covariant tensor vector and the scalar part. So this h mu nu cap is a tensor, a mu nu is a vector, and then b and phi are your scalars. And these are the traceless transverse and traceless and transverse conditions on the vector and tensor modes, and they cancel the degrees of freedom. In order to match the degrees of freedom on the left and the right hand side, you need these conditions, and this is the maximal decomposition that you can have covariantly for this H medium. So I want to see what the degrees of freedom look like in this theory. So the action I will consider is a very general one. So in addition to the Einstein-Hilbert lambda term, which is composed of the Ricci scalar and a cosmological constant, I will have a non-local R squared piece, a non-local traceless Ricci tensor piece, and a non-local wild tensor piece. And they will all be parameterized by these unknown functions f1, f2, and f3, which are unknown at this point, and they must be determined and fixed around a particular background, such that there are no new and no ghost degrees of freedom around that particular background, other than the spin 2 traceless transverse graviton. And just like before, these unknown functions are infinite, have an infinite series of derivatives all the way from 0 to infinity. And for dimensional reasons, I need to have a new mass scale, ms, which I will assume it's less than the Planck mass. And this is the scale at which these higher derivative terms become more and more important. So around a general background, the quadratic action is very complicated, and you can split the degrees of freedom into these two scalars, one vector and one tensor, and you will have a generalized kinetic matrix around an arbitrary background, where in principle, around an arbitrary background, all these components are non-zero. You will have off-diagonal, and off-diagonal components will also be non-zero. So in order to simplify the analysis, you need to fix the background first. If you choose a flat or DS or ADS spacetime, then all the off-diagonal components they actually identically drop out, and you will only have a diagonal matrix, and there are no more mixing terms between different scalars or vectors and tensors, and you will have kinetic and mass terms only for this one scalar mode phi and this tensor mode h cap, and no mass and kinetic terms for the scalar p and the vector. And it is indeed possible to constrain this f of box around a maximally symmetric spacetime like flat ds or radius, so that you don't have any new degrees of freedom or ghosts. And I'll get to an example of that soon. Around non-maximally symmetric backgrounds, the analysis is really complicated. Even if you fix these, the conditions that I chose a few slides before, where the wild tensor is 0, and even if you fix that the covariant derivative of the traceless Ricci tensor is 0, and just that the only thing that separates me from maximal symmetry is the presence of a non-zero traceless Ricci tensor. Even if you impose all these conditions, the kinetic matrix has all the components non-zero. You will have kinetic and mass terms for all the SVT modes, and you will have a non-diagonal matrix with all 6 mode mixings present. So you will have a mode mixing between B and phi, between B and A, between B and H cap, between phi and A, phi and H cap, and A and H cap. You will have all the 6 mode mixings present, even after you assume these conditions on the background. And but it is easy to see that all these new terms in the kinetic matrix that take you away from maximal symmetry are directly proportional to the traceless Ricci tensor. And in the limit where the traceless Ricci tensor goes to 0, you go back to ds ADS, and we recover the known results that were done a few years ago. So instead of taking an action which has 3 different non-local terms, I'll just consider an action which has only one non-local term, and I'll choose that non-local term to be the one coming from the wild squared piece. So I take the action to be Einstein-Hilbert with a cosmological Einstein-Hilbert with the Ricci scalar with a cosmological constant and a non-local wild squared piece. In this case, around a maximally symmetric spacetime, it could be ds or ADS, the quadratic action looks like this, where you have a only two non-zero components for in the kinetic matrix, one for the phi scalar mode and the other for the h mu tensor mode. This tilde means that it's canonic. These are canonically normalized fields. So the kinetic kinetic term for the scalar has no UV contribution because there is no information about this non-local function f of 3. This is just the local contribution, but a non-local contribution comes in the tensor sector. In this case, in square parenthesis, you have this function f of 3, which modifies gravity in the UV sector. So this is what we should look at. So you have the usual IR pole at box equals to r by 6 in the tensor sector, but you have a new UV contribution coming from this unknown function f of 3. And this is what we should constrain so that there are no zeros coming from this part, because if you have new zeros from this part, then you will have new degrees of freedom, and also definitely you will have ghosts. So this is what we want to avoid. So again, to avoid that, I will just impose that this is an exponential of an entire function, which is the Weierstrass product theorem. If I constrain this to have the form of an exponential of an entire function, then this term will not introduce any new zeros, and therefore it will not introduce any, and therefore you don't have any new degrees of freedom in the theory, and therefore you don't have any ghosts as well. And you just invert this relation, and you get the function f of 3 in this particular form. It's given by this exponential minus 1 divided by box minus 2r by 3. So it's just about the question is just about finding a particular form for this function f of 3 such that there are no new degrees of freedom. And for an Einstein-Hilbert plus non-local Wild squared around maximally symmetric spacetimes, this is the form of the function that you need to have such that there are no new degrees of freedom or ghosts other than the usual spin 2 traceless transverse graviton. Another example is, instead of taking a non-local Wild squared, you can take non-local R squared. So you have Einstein-Hilbert, the cosmological constant, and a non-local R squared term. In this case, we want to see what the degrees of freedom are around non-maximally symmetric backgrounds with the conditions that I chose a few slides ago, where the Wild tensor is 0 and the traceless Ricci tensor is non-zero, and covariant derivative of the traceless Ricci tensor is 0. If you impose these conditions in the equations of motion that you get after varying this action, the background equations of motion look simply of this. They have this simple form where where this omega is just a number which is mp squared plus 2f0 r bar. R bar is the background Ricci scalar, and f0 is the first coefficient in the expansion of this f of box. So there are three solutions to this background equation of motion. One is where you can have the omega to be 0 but s bar non-zero, or the other way around, or the third case is where you have both 0. So if you have a traceless Ricci tensor which is non-zero, then you are not in a maximally symmetric spacetime. And this is the first thing that I would like to consider. In this non-maximally symmetric spacetime, the quadratic action, again, has a very simple form. It has only one scalar degree of freedom, which is psi, which is actually a combination of the two basic degrees of freedom, phi and h cap, where phi was a scalar degree of freedom and h cap was a tensor. And by the way, psi is also gauge invariant because phi and h cap are gauge invariant. So if you have the quadratic action that looks like this, which describes only one scalar degree of freedom, you have the kinetic operator, simply it's given by f of box. So the propagating or ghost degrees of freedom depends on the form that you choose for this f of box. If you choose f of box to be a constant, simply a constant, then you don't have any kinetic term for psi at all, and that's not, so it will not be propagating. And if you have if you choose an f of box where you have one pole, sorry, not one pole, if you have the factor in parenthesis gives one pole in box minus m squared if epsilon is equal to 1, and no pole at all if you have epsilon equals to 0. So epsilon is just a parameter that uh, interpolates between these two options. And I add an exponential of an entire function over here so that I modify the UV structure, but at the same time, I don't introduce any new zeros in the kinetic term. So if I choose epsilon equals to 1, then I will have only one pole at box equals to m squared for some mass m. This m cannot be fixed at this point. At least if I impose the condition that I don't want any ghosts, then that condition itself is not sufficient to fix this mass m. But let's just suppose that there is some mass m. Then you will have just one pole at box equals to m squared, and the theory is ghost free around this non-maximally symmetric background. Now, we still have two different cases in which you can solve the equations of motion, and both of them have correspond to maximally symmetric spacetimes, but they are of different character. So if you have S bar equals to 0, then you will be in a maximally symmetric spacetime. But the fact that in one case omega is 0 and in the other case omega is non-zero, that will actually lead to two physically distinct maximally symmetric spacetimes. And you can see that from the uh, quadratic action and the degrees of freedom that you have around these two backgrounds. So if you compute the quadratic action for, if you take this action, which is non-local r squared plus Einstein Hilbert lambda, and you compute the quadratic action around these two maximally symmetric backgrounds. So in one case where the this factor omega is non-zero, in this case you will have a diagonal, you will have a kinetic matrix which is diagonal, but it will have both a scalar mode phi and a tensor mode h cap. But in the case where omega is 0, you have a diagonal kinetic matrix, but it does not have any tensor mode at all. So in a sense, it's a special kind of ds-ADS vacuum where you have only a scalar mode. And this happens just because the Ricci scalar, which is related to the cosmological constant, is also finely tuned to the first coefficient f0, which is the first coefficient in this power series expansion of f of box. It's exactly because of this tuning of parameters that you will identically, the tensor mode identically just it vanishes from the quadratic action, and you will have only a scalar mode. This was so actually in both these cases. I'm not showing it in this case, but it is easy to show that you can constrain these form factors f of box so that there are no ghosts or no new degrees of freedom around both these maximally symmetric backgrounds. And these ds-ADS vacua are actually different because they have distinct spectra. And this was done before in 2011 by Pope and Liu, where they take which they call critical gravity. So in this case, you have stealth theory, which is r plus r squared plus r mu squared plus a cosmological constant. So it's stealth theory plus a cosmological constant. And in this case, after adding a cosmological constant and for a particular tuning of parameters between parameters alpha, beta, and lambda, they were able to make the massive spin 2 mode massless, and they were able to get rid of the scalar degree of freedom. So what I did in this case in non-local theory is sort of a higher derivative generalization of critical gravity, where you can have some special vacua, special ds-ADS vacua, where you have degrees of freedom which are different, which which are degrees of freedom which are in the theory which are distinct from usual expectations, because you would typically expect to have gravitational waves, you will have tensor modes, but it is indeed possible to have a particular tuning where you do not have tensor modes. So this brings me to the end, where uh, you can have a high derivative non-local gravity model which has a non-local r squared piece. For instance, it can be made free from ghost-like instabilities around non-maximally symmetric backgrounds, and this involves choosing a suitable function f, which can be chosen. And upon a critical tuning of parameters, one can have special vacua, special maximally symmetric vacua, which have physical spectra which are different from usual expectations, in the sense that you do not have tensor modes in propagating tensor modes, at least at the linearized level of equations of motion or at the quadratic level of the action. And if you consider much more general actions which have non-local R squared, non-local Ricci tensor squared, and non-local Weil squared, in this case, you will have scalar vector tensor mode mixing for all the 6 different modes around non-maximally symmetric backgrounds, and it is challenging to find stable cost-free solutions in these cases. But still, there are open questions. Obviously, the first one is in high derivative gravity, you will have a black hole or black hole-like objects. So what is the case in non-local gravity? Are black holes or black hole-like objects in high derivative non-local gravity stable with respect to generic perturbations? This is, again, an open question. And another important point is the form factor that I chose throughout for all the different cases for ds-ADS spacetimes or for non-maximally symmetric spacetimes. I followed a perturbative approach where I first choose a background and then I do perturbations around that background, and I compute the quadratic action, and then I fix the form factor f, which depends on that particular background. But we know that, for instance, GR is background independent, so naturally it would be much nicer if we can find a background independent approach towards finding these form factors, and that's again an open question. That brings me to the end of the talk. Thank you.
Great stuff. Thank you so much for that. Lovely talk. Do we have questions? Do people want to unmute themselves and ask questions? Or type them in the question box alternatively?
I had one. Yeah, Tessa here. Hi, Shubham. I was just wondering, in your talk, what exactly was the definition of non-local? And the reason I asked that is because lots of the functional forms you were presenting there look rather different to what I've seen described as a non-local theory in lots of other contexts. So, for example, the sort of Maggiore groups have done a lot of work on non-local gravity models, and they always have inverse box acting on some objects. And perhaps sort of sloppily, I had kind of assumed that was an intrinsic part of what it takes to be a non-local model. But looking at your expressions, that doesn't seem to be the case.
Yeah.
So what is it that makes this non-local, I guess?
Yeah, well, there is one way of looking at it. So, well, it's because you have an infinite series of derivatives, although this is analytic, so there are no inverse powers of box over here. It's only, it starts from, it only has a 0 or positive powers in box. You don't have box inverse.
Yeah.
But it is, one way of looking at it is, well, you can kind of write it in an integral form as well. So these, for example, you have these kinds of operators in p-adic string theory, and it is possible to rewrite the equations of motion for these theories in a form which is integral. So so you rewrite the differential equation of motion in an integral form, and it depends on space-time points throughout the space-time. So in that sense, it's non-local.
Okay, that ties in with my intuition of the kind of theory. I guess it just maybe it wasn't supposed to be obvious from the equations you were presenting that there was that rewriting.
Yeah,
right,
you can.
Thanks very much.
Yeah, sure.
Cheers.
Any other questions? Okay, if not, if no one else has any more questions, so I'll thank you again. And I think if we now leave you with the students, so the students will stay on and ask a few questions without us there to watch over their shoulders. Yeah, thank you so much. And I think let's because it's all a bit of an anticlimax. I'm going to ask everyone to unmute, and maybe we can all, if we could all just give a round of applause.
Thank you.
Next week for the next Cosmology seminar, and students, if you stay on and ask some questions. Thank you so much again.
Yeah, thanks for giving me the opportunity to talk here.
Great, thanks very much.
Thank you, thanks, bye.
Bye.
Also, don't forget the live streaming is still on if you're asking questions and stuff.
just to let people know, the